who's been a very, I would say, I mean, inspiration for most of us who look at him as a leader in the field. And I mean, he's at NCAR, currently deputy director of the Research Applications Laboratory, one of the biggest labs in NCAR. Dr. Rajesh did his bachelor's and master's from India and went on to get his PhD from Hamburg. And from 2013 onwards, he's been associated with NCAR, right from AMC postdoctoral program right to deputy director of RAL. And he has been very instrumental and one of the most efficient, one of the most innovative, and one of the most productive personalities in the field of atmospheric chemistry. Uh, he's been leading quite a lot of initiatives on air quality forecasting, model developments on many fronts. One of the things one could probably point out is he's been founder and co-chair of the MAP AQ activity of WM and ICAC, and apart from that, he has been involved in numerous such activities. And of course, needless to say that he has more than 100 papers to his credit, and he's been a lot of committees as well. We can talk about MUSICA framework and take us through this newly developed or probably in development phase, the model and how it works and how NCAR sees that in as in the days or years to come. So over to you, Rajesh. Thank you.
Okay, can you hear me? Is it on? Okay. Yeah, thanks a lot, Gaurav. I'm flattered for such a nice introduction. So I'm going to talk about this new modeling framework, which we call as the next generation atmosphere chemistry modeling system. And of course, I have done nothing to build this system. There is a big team, and I folded everybody's name in MUSICA team. So we have a big team who is working on building this model. They have been working on it for the last 4 to 5 years. I'm going to tell you about what was really the motivation to build this system. What are some of the best things that we have done for the system? What are our future plans? Our collaboration with IITM. So we are starting a collaboration with Sachin's group to develop this system further and test it over India, especially for air quality predictions in Delhi. So the outline of my talk is I would start with a little bit of model fundamentals, because I know that the scientists in the room, they do not need a couple of slides on understanding what a model is, but I also see a lot of young people, students here. So I'll tell you a little bit about what a model is, why do we need models, and then some results based on the MUSICA simulations, what type of software architecture we have for MUSICA, and then I have a take-home message slide at the end. Okay, so this is a question for all the students in the room. What do you think? What is a model? And anybody, you don't have to shy. Even if you don't know the answer, you don't have to be correct. We always start with wrong answers. So anybody, if you want to say, for easy understanding, what is a model? And I'm not talking about atmospheric model. In general, what is a model? Not the one that really works, but just a model. Yeah, come on, don't be shy. I know that you are talented people. All right. Anyway, no problem. It's fine. If no, we don't know, we don't know. That's okay. So model is a simplified representation of a complex system, right? That is the simplest definition of a model. We try to simplify things as much as we can. You can see here, you have a real car and then you have a car model, right? So similarly, we do things in atmospheric science. So the next question is then, what is an air quality model? So it is a simplified representation, but how do we simplify such a complex system to make it a model? And because models are simplified representations of the atmosphere, there is a famous quote which says, all methods are wrong, but some are useful. So let's see what is a model. What we try to do is, we know the atmospheric processes, they occur at a range of spatial and temporal scales. If you take, for example, the hydroxyl radical in the atmosphere, its lifetime is 1 second. And if you take CO2, its lifetime is more than 100 years. So you have to represent species that go from such a small lifetime to such a large lifetime. And then you can have processes that can start at the floor of this room, but they are not strong enough to reach the roof of this room. And then you have processes, hemispheric exchanges. You have a pollutant that is emitted in India and it can go to the South Pole or North Pole. So it's a very, very complex system. It means if we want to resolve all the processes, we have to have spatial scales of less than a meter, and you need to have time steps that is less than a second. But if we build such a model, then we are not going to run anything. So we have to simplify a lot of things. So that's what we do. So say, for example, what you see here in this figure is we try to divide, and that has been the traditional concept. Now we are changing it. I'll show you some examples in the presentation today. But you divide the atmosphere into grids. And then if you just take one box, this is how one box looks like, right? So the room we are sitting in, we can consider this as a grid box of a model, right? So if you consider this room as a grid box of the model, then from the surface, you have the emissions that are happening. So at the floor, we have all the transport sector emissions, we have all the industries, we have all the residential areas, all the agricultural burning that is taking place. So that is all happening at the floor of this room. Then, because we also get the solar radiation, so the surface is heated. With that heat, you mix the pollutants up. So they go up in the atmosphere. They participate in chemical and aerosol processes. And similar to the spatial and temporal scales that I was talking about, there is a lot of complexity in the chemical and physical processes. So you need a lot of parameterizations to solve those complex physical and chemical systems. But then if your grid is such that the floor and the roof of the room, this is the difference between the model levels. And if you have a process, if you have a motion that is starting from the floor, but it is not reaching the roof, that is called a subgrid scale process. So it is still going to affect the chemistry within the box, the physics within the box, but we do not have the spacing to resolve it. And so we come up with parameterizations to resolve those processes. And then if we just take this room, it is just in isolation. And we know that the winds are coming. If the winds are blowing this way, something will be coming from the next room, leaving this room, going there. Same thing will be happening in this direction and this direction. So when you put these rooms together and you cover the world, that is your model. So this is an air quality model, so you need a lot of input. But modeling is just one part of the bigger ecosystem that we need to advance our understanding of the atmosphere. So whenever we do atmospheric science, what we do is we always start with observations. Of course, we have some prior knowledge because we have basic understanding of physics, chemistry, biology, etc. And they are also valid into the atmosphere. So we start with observations. The observations are always the basis of our fundamental understanding of the atmosphere. So observations, they drive our process models and fundamental science. And then what we try to do is when we have that fundamental knowledge, then we try to represent those in the form of mathematical equation. And those mathematical equations are then turned into computer codes. And that is what our codes are. I think I'm getting a lot of echo. Should I put it a little bit down? Let us see if this is better. What you do is you have models, and then the community comes together. But you also have data assimilation, which is an important component, because as I said, it means we have to represent the subgrid scale process. We are not resolving everything. So by design, a model is expected to have errors and biases. A model can never be correct because we are not capturing all the processes explicitly into the model. And data assimilation is the way to nudge these models towards observations. And so basically data assimilations helps us better constrain initializations of the model. It can also be used for inverse modeling of emissions and a lot of things. So model is just one component of the larger ecosystem that we use to advance our understanding of the atmosphere. And there are many things for which we can use the model. You can use it for predicting past, current, and future. You can use it for forecasting, like Sachin's group has this air quality early warning system for Delhi. It can be used to explore interactions between weather and chemistry, which is very, very important in Indian conditions because we have very high aerosol load. And then there are a lot of things that are on the slides. You can read those. I don't have to go through everything. But basically, these are the tools to kind of evaluate our understanding, expose ourselves against new observations that we collect, and then improve the models further. So it is kind of an iterative process. So on this slide, I'm going to tell you about the current atmospheric chemistry modeling ecosystem that we have at NCAR and also at several other institutions. So we have multiple dimensional models. And historically, some of our model developments has been driven by the availability of computing power. So we have box model. So if you go back to the example of using this room as a grid box, if you just focus on this room and you don't worry about transport, what is happening, what is not happening, then we call it a box model, right? Now, if you are interested in, say, for example, aerosol radiation interaction, and you stack a lot of rooms one above the other to the top of the atmosphere, you start looking at the solar radiation coming down, right? So now we are dealing with the vertical dimensions. Those are one-dimensional models. Then we have two-dimensional models, which were really useful when we had the ozone hole issue, because we had transport of CFCs from the tropics to the polar regions. So we needed models which can capture this latitudinal transport and the vertical transport of CFCs in the atmosphere. So those were really, really helpful at that time. And then finally, because air pollutants are short-lived, we need to capture the spatial heterogeneity in all the three dimensions. We developed three-dimensional models. So at NCAR, we have developed all these type of models, the 0D, 1D, 2D, and 3D. And so here is just a graph showing that in a box model, how you look at the chemical evolution of a plume. Then we have regional models like WarpChem, where you just focus on one particular region of the globe and you try to look at the air quality or physics or weather parameters, etc. And then you have the global chemistry transport models, Earth system models, which are really used for climate assessments. A lot of Earth system models, including the IITM Earth system model, they contribute to IPCC assessment every 5 years. I think the community is now preparing the CMIP7 experiments that are going to be the basis of the next IPCC report. But so if we already have the models, then what is the need for the next generation model, right? One can say that, okay, you have so many models. If you want to do box, you can do box. If you want to just look at Pune, you can look at Pune using WarpChem. If you want to look globally, you have CESM. Then what is really the need for a next generation model? And so the reason is, when we are talking about these models, they are either focused only on a particular component of the Earth system, like atmosphere. So when we say WarpChem, it is an atmospheric model. The oceanic processes you have to prescribe. You just prescribe the sea surface temperature, and then you look at the impacts of that on atmosphere. So these are only representing some parts of the atmosphere. But the reality is that everything is connected when we look at the system as a whole. We do have the global Earth system models like CESM, the example that I showed in the last slide. But then because of the computational efficiency reasons, we cannot operate CESM at 1 kilometer resolution everywhere we want. And so to address that problem, we have to be innovative. We need a model that can go down to 1 kilometer resolution when needed in particular areas. Say if we are interested in looking at the impact of Pune on the global atmospheric composition, we need to resolve emission sources in Pune. And so we need to go down to 1 kilometer resolution in Pune, and then maybe we can run the rest of the globe at a higher resolution. So really the motivation for developing this model is right now we are in this framework. We have different scales. So you look at the scale here goes from hours to centuries, and the spatial scale goes from local to global. Even though we are capable of simulating everything, we have a different model for everything. It also becomes a challenge from a management perspective. It also becomes a challenge from redundancy perspective. So what we are trying to do is we are trying to get away from this paradigm, and we are trying to go into a new paradigm where chemistry and aerosol are simulated at a different scale but in a coherent fashion. And that is really the basis of this MUSICA model. So what we are trying to do is we are trying to put that into an Earth system model, which is our community Earth system model. It's a NCAR flagship model. And so this is the part that we are developing. This is the part that we call as MUSICA. It is the chemistry and aerosol suite, where we have a gas phase chemical solver, photolysis scheme, aerosol processes, emission, and other air quality related processes. And then we have physics suites. Now, as we are designing this system, there are several processes that are relevant to chemistry, but those are physics processes. Say, for example, turbulent mixing, cloud microphysics. So the turbulent mixing and cloud microphysics. So what we are trying to do in the new design of this system is, instead of doing those in a silo in the chemistry part, we are trying to do those under the physics suites, so that all the process should be done in a parameterization where it belongs. And then we are building a standardized interface so that this part can be coupled with any atmosphere model. It doesn't have to be only the NCAR models to which this MUSICA system can be coupled. It should be able to, one should be able to couple it to, say, if you build an atmosphere model here, people here should be able to couple MUSICA to that atmosphere model. So making it independent of the NCAR ecosystem. And then we have the coupling architecture for connecting it with the different other components of Earth system, as well as data simulation, evaluation packages, etc. So you can scan this barcode and it will take you to the MUSICA website. I have this barcode in multiple slides. So if you miss it, don't worry. If you don't scan any and you need information, send me an email and I'll share the website with you. We have so far developed two versions of MUSICA, version 0 and version 1. The only difference between these two versions is the dynamical core. In the version 0, we are using a hydrostatic dynamical core, which is based on spectral elements. And in version 1, we are using MPAS dynamical core. MPAS stands for Model for Prediction Across Scales. And this is a non-hydrostatic dynamical core. So basically, the thing is, you can apply MUSICA V0 at scales more than 5 kilometers or higher. But if we go down to less than 4 kilometer resolution, we really need to have the non-hydrostatic dynamical core, because at those resolution, the pressure gradient in the atmosphere is not simply balanced by gravity, and you need to take into account other forces that lead to vertical acceleration. So I'm going to show you some results, and these are some of the studies that our group in atmospheric chemistry and observations and modeling lab has done over the last few years. Because we live in the US, so we started with things over the US. So we come up with this. This was our initial domain for MUSICA V0, where we are running the rest of the globe at 100 kilometer resolution. And over the US, we go down to 14 kilometer resolution. But it is not a step change in the resolution. We're not going like directly from 100 to 14. So I think we go in steps of 8 kilometers, right? So if this is 100 kilometer, then this is 92 kilometer, and then 84 kilometer, and so on. And that's how we go gradually make changes in the grid to go to 14 kilometer resolution. Here are some configuration details, and there are a couple of papers that have been published evaluating this model configuration in the literature. We not only have the grids over the US, we actually have many different grids. There is a grid available over India as well, and unfortunately, I couldn't find that figure quickly to include in this slide. But if you go to this this website, you can actually also find the India grid. This is one of the reasons, like one of the cases that we demonstrate using this model. We know that air quality in the US has been improving for the last 10, 15, maybe 15, 20 years, because it was a big problem in 1950s, 60s. It was the same amount of problem in the US as we have in Delhi now. And so we have come a long way since then to address anthropogenic emissions in the US. It is not that we have eliminated all the anthropogenic emissions. It is more like it's a combination of the mitigation efforts and transfer of a lot of manufacturing to Asia. So the air pollution problem in Asia grew because a lot of manufacturing came to Asia, and it decreased in the US because there is no manufacturing, very little manufacturing now, but also they have worked on improving technologies in the vehicles, in the power plants to control the local emissions that were contributing to that problem. One important component that leads to a lot of issues in the US is the wildfires now, because there are a lot of forests. With the climate change, there are a lot of droughts that are leading to dry vegetation, and we have huge wildfires. And so our summer season, especially in the western half of the US, is really bad air quality. And so in the red here, you see a particular WRF-Chem domain that we would normally run over the US. And so when you are simulating these wildfires, the smoke will be simulated, the transport and dispersion of the smoke. And once it leaves the domain boundary from WRF, it is lost, it is gone, right? But then there are sometimes cases when this can circulate back into the domain. And so this was one of the cases where the smoke left the domain boundary, it went into Canada, and then it came back into the US. So these type of processes, we can also simulate with the WRF-Chem model, but because we are providing the little boundary conditions. But remember, when we are providing little boundary conditions, they are based on a global model, which is not resolving the wildfires at the resolution that we are doing now. So the smoke is artificially diluted, right? So you will have transport of lesser smoke to Canada, and then less smoke will come through the boundary condition. So you can capture the phenomena, but you can better simulate it with a model like MUSICA. And then when we compare MUSICA with WRF-Chem, there are two configurations of WRF-Chem, but with one of them, MUSICA provides almost identical results to WRF-Chem. So some of the differences, other differences could be because of how we define our vertical grids, what chemical mechanism we use, what type of emission inventories we use. But in general, the ozone simulated by MUSICA was within the range of the ozone simulated by WRF-Chem. So here I'm going to show you an animation. I can get that working. Can you play that video? It's playing already. So this 2020 was the worst wildfire season in the recent years in the US. September 2020, so you can see all the carbon monoxide that is emitted by the wildfires in the western US. And then pay attention to this. When you get close to 15 September, you would see a huge smoke plume that actually went over the US, over the Atlantic, and went into Europe. That was such a large wildfire activity. So you simulate these things in the global models as well that do not have variable resolution, but the amount of smoke that goes into the atmosphere, that is transported downwind, that is smaller. That magnitude is smaller, and that leads to an underestimation in the exposure studies that you do later. Here is another example of stratospheric intrusion simulation by MUSICA. And if you can play the video, okay, it plays now. So you can see that during the same period, now you do not see a lot of stratospheric intrusion, but it was very interesting that when we had those huge wildfires, you see that there was also stratospheric intrusions. And we do not know if there was a feedback because of the wildfires, because if there are huge wildfires, they release a lot of heat in the atmosphere. There is a lot of vertical motion. We do not know if there is a compensating downward motion that is bringing down stratospheric ozone in near the surface. And so this is something that we just saw in the MUSICA model, because we have interactive chemistry and dynamics. and because MUSICA allows the stratospheric and tropospheric chemistry to be simulated. So this could be another interesting area that can be studied with MUSICA. We have also applied over Africa. And so this is our domain, and compared it with a 20-kilometer simulation from WRF-Chem. So for most of the stations, the WRF-Chem and MUSICA simulations in terms of carbon monoxide now are similar. There are some differences, like if you look at this particular station, which is Cape Point, it is here. And you can see like how much difference a 5-kilometer resolution can make. WRF-Chem is run at 20-kilometer resolution, which is in blue here. Black is the observation, and MUSICA is run at 25 kilometer. So when we are in coastal areas, even a small difference in the resolution becomes very, very important. At all the other sites which are more inland, MUSICA and WRF-Chem have similar performance. So we have to be very, very careful when we study coastal areas. Coastal areas are generally the population hubs. Right? If you look at most of the major cities, look at Mumbai, Calcutta, Chennai, New York, all of them are coastal cities. So resolving coastal areas is very, very important as well. Okay, so then we had a postdoc, and he was from Korea. We had a Chorus AQ campaign. And so he applied MUSICA over Korea to look at the impact of resolution on the chemistry and whether resolution matters for inert species like black carbon, or does it only matter for reactive species like ozone? So this is just kind of a demo. It's not a model result, but this is the hypothesis that that Dusong started with. Like, okay, if you have a global uniform grid, you might have a 7 ppb. If you average all these numbers, I have not done it, but I'm sure you will get to 7 ppb. And if say this is the urban center, this is what you are going to measure, it is going to see 7 ppb. Whereas in reality, you can have large heterogeneity in those mixing ratios. So the question was, if we have this variable resolution model, can we capture this type of distribution? And so he actually did experiments with these different resolutions. He ran everything at 112 kilometer resolution. Another grid he took at 56, 14, and 7. We don't go below 7 because we have hydrostatic dynamical core in the model. So this is the Chorus AQ campaign. You see here a lot of the flight paths. He did simulations with and without applying the diurnal profile of emissions, like the two profiles that you see here. In blue, you have the diurnal profile for area and point sources. In red, you have the diurnal profile from the mobile sources. So we were trying to look whether resolution is more important or the diurnal variation of emissions is more important. And so you can see here in terms of black carbon concentrations at the surface. So at 112 kilometer resolution, this is how CO looks like. It looks like just one box where everything is same within the city. And then as you start to increase the resolution, you start to kind of see more the spatial variability that you see in an urban area. There are more higher values at the center. As you go away, you move away from the emission sources, the concentrations naturally decrease. And then we look at black carbon because black carbon is chemically inert. It doesn't react with anything. So the idea is, if you take the simulations at 7 kilometer resolution and you grid it back to 112 kilometer, do you get the same result? And this is the regridded part. Now, if you compare this figure with this figure, you can say that they are more or less similar, right? So for chemically inert tracers, when we are doing it, of course, it matters for the exposure. But when we go down, we average things at that scale, the resolution doesn't matter. Now let us look at the same thing for ozone. So this is for ozone now, the same figure, the ozone distribution at different resolution. And as you see that at 112 kilometer resolution, everything looks the same everywhere. But then when you go to 7 kilometer resolution, you see the nighttime titration of ozone because of a reaction with NO. And now when you regrid this back to that resolution, you do not get the same map. There are more differences. So the resolution really becomes important for reactive species or the species that form in the atmosphere. It is going to be very important for secondary organic aerosols when we have those. And so it becomes really, really important to have those variable resolution for appropriately characterizing the exposure of public to air pollution, because that is one of the end goals of our air quality research. Okay, here looking at the diurnal cycles of different species, like this is, and these are emissions, and this is now the diurnal profile of NO. This is NO2. This is ozone. So we see large variability. Means different colors here. The different colors here, they represent different resolutions, right? And you see dotted lines and solid lines. Solid lines are with the diurnal variation of emission accounted for, and the dotted lines are with no diurnal variation. So one thing is you see large variability in the solid lines, which is higher than the difference between the solid and dotted lines of the same color. So this tells us that resolution is more important than accounting for diurnal cycle of emissions. Another thing is the nighttime titration also is very, very different as a function of resolution. Because if you have high resolution, you resolve NOx better, you have higher levels of NOx, the reaction rate of NO plus O3 goes up, and you eat up a lot of ozone, have very low ozone. If you are diluting it over a large area, you have very little NOx to react with ozone. Okay. But then the interesting part is, so we had aircraft observations over Seoul. And so we try to see, like, okay, we see this difference is in the model. This slide back here, we are just doing things in the model. We do not know whether they are correct or wrong, right? It is just a model intercomparison exercise. So we need to compare our model with observations to see whether we are really improving things with resolution, or we are making things worse. And that's why field campaigns like the WIFEX campaign that you do at IITM and all the other meteorological campaigns that you do are so important. So we look here, and so this part is ozone, the vertical distribution of ozone. And remember, the blue color is the coarsest resolution, 112 kilometer resolution. And the pink colors or the purple colors are the highest resolution, which is 7 kilometer. And these boxes are from the observations. So you see here for ozone, even though all the modeling configurations have large errors, right? The domain with the coarsest resolution performs the best. And you look at NO2, NO and NO2, which are more primary pollutants, the domain with the highest resolution performs the best. Right? So there is no right answer. You do a lot of work, you build these models, you confront them against observation, then you really realize what are the types of errors you are making. Now the question is our vertical grid spacing too coarse in the model, right? Because the titration of the ozone is happening in the boundary layer, right? So if we have 2 course of a model vertical layer, everything is considered well mixed into that layer. So here, the observations are telling us if you are getting 80 parts per billion of ozone at about 400 meter resolution, it means the surface layer is decoupled from the layer that the aircraft is measuring. And we are not able to resolve that coupling with the vertical grid structure that we have. It could be one possible reason. We do not know. It's an hypothesis, right? But that's why observations are so critical. That help us understand what errors we are making. How do we improve our models further? But then,
did you look at black carbon?
I think we might have, but I have to look at it. But yes,
black carbon on reactive.
Yes.
Relationship. In the reactive itself,
So the species that are directly emitted, like NO, so I would expect to see a similar performance for black carbon that we see for NO. So then that's why we have data assimilation, right? Means model improvement is a long-term process. We do the modeling, we confront it against the observations, we learn what is right, what is wrong, then we try to improve it. It's a long-term process, right? But if you look at every country in the world right now is going after actionable information. And that is because we now have models which can produce some information, right? But when it comes to decision making, people have to make decision today. They cannot wait 10 years to improve for the model to improve to make decisions. And data assimilation is one of the techniques to push model to more towards observations and see if we can provide better forecasts to decision makers. Data assimilation also helps us better understand in what regions of the world the model is making larger errors, and which tells us like, okay, this is the region where we need to focus on. Maybe we need to design a field campaign to go and observe that region and see what can we do better in terms of modeling. But anyway, so this is one of the data assimilation experiments with the assimilation of MOPIT carbon monoxide profiles done by Benjamin Goubert. And you can see that our MUSICA run, the default run is in blue, the observation from the Chorus AQ in black, and by assimilating the MOPIT satellite. So remember, we are assimilating CO that is observed by the satellite, and we are comparing it with what the aircraft measured. So it's an independent verification. But after assimilating the satellite CO profiles, we are able to push MUSICA more towards MOPIT. And then it is very important because we have a geostationary satellite constellation. 2 of these have already been launched. Tempo satellite has already been launched. GEMS has been providing observations for more than a few years. And that's where models like MUSICA comes in very handy, because you have 3 focus regions. And so in MUSICA, you can have 3 different domains that are high resolution over these 3 regions, and you can run the model over the rest of the globe at a coarser resolution. And so here we have like some observations from Tempo and GEMS. You can see the benefit of having a geostationary satellite. So earlier, like satellites like TROPOMI, OMI, MODIS, VIRS, all these are polar orbiting satellites, which means they only come once a day. They see the Earth only once a day. And say, suppose if the MODIS is or the OMI is coming at this day, this is the distribution of tropospheric column NO2 that the polar orbiting satellite would see, right? And over the last 20 years or so, we have used those measurements to come up with inverse modeling of emissions. We have used them to look at ozone production efficiency changes, etc., right? But if you look only 4 hours later, the distribution of the tropospheric column NO2 is completely different, right? So the geostationary satellites, they help us better monitor the changes in tropospheric activities. Now, we have to be careful with the satellites, right? Sometimes we get too excited. We say that we have a geostationary satellite. It is making measurements throughout the day. We get information about diurnal variation. But we must always remember that these are column integrated quantities. We do not have the vertical information in the satellite observations, right? So a big part of the research goes into how do you connect the space measurements to the surface air quality? And that's a big question people have been trying to answer for a long time. I do not know what to see in the TAMS, but in the GEMS, but you can see over China, you can see significant differences between the 11 o'clock and 5 o'clock overpass. So these are the type of measurements that are becoming available. Soon we will have Sentinel-4 launched, and we will have this thing over Europe as well. So with these measurements being available, we need a modeling system that is able to resolve these source regions in greater detail.
Rajesh, when you assimilate column in the previous slide, are you fixing the concentration or are you fixing the flow?
This one? Yeah, this one we are fixing the concentration. And here, because MOPIT has a profile retrieval. So this one is not a column retrieval, it's a profile assimilation. But when we assimilate the column, what we do is we make an assumption that the vertical profile simulated by the model is correct, which could be a wrong assumption in some cases, which could be a right assumption in some cases. And so we scale that vertical profile according to the assimilation to match the model and observation. But we assume that the vertical profile simulated by the model is correct. So we have come up with this MUSICA configuration. Like we have 3 different high resolution regions within the model. And I think we have done some simulations using this configuration, but I do not have any results from those. it is very similar thing, like looking at the impact of resolution on emissions. You are at coarser resolution, you artificially dilute everything. You are at higher resolution, you resolve everything. And then this is the simulation over East Asia. And this is again kind of showing that when you are at 100-kilometer resolution, this is how the NOx distribution looks like, and you better resolve surface NOx in 12-kilometer domain. When you look at ozone production, ozone is a very interesting species, right? You look at 100-kilometer resolution results, you get similar values of ozone. Irrespective of whether you are at 100-kilometer, you are at 12-kilometer, we do not know, is it because of the compensating errors? We do not know if is it because we are moving at a diagonal line on the ECMA diagram when we are changing the VOCs and NOx concentrations. But it is very interesting species. It is so interesting. You do see some high resolution features, but overall, if you give this image to a fifth grader, they say these are the same things. There is no difference, right? We also tested whether we can use MUSICA for supporting field campaigns, like we had Asia AQ that happened recently. So we employed MUSICA in forecasting mode to forecast the transport and dispersion of pollutants, including simulating their atmospheric chemistry. And so again, the objective of Asia AQ was really again to see how do we go from space to the surface. Those measurements and how can they be connected. These were the study regions for Asia AQ: Thailand, Taiwan, Korea, and Philippines. These were some of the example flight trajectories, and you can also look at the agencies that were involved, the instruments that were there. So these were the flight trajectories for this campaign. And this is JAMS daily NO2. So you can see that there is a large day-to-day variability. And so when you are doing a campaign, you have to make decisions. You can talk to Anup. Anup can tell you all about how do they go about chasing pollutants in different parts of the atmosphere. So it's a tricky decision that you have to make, but models can be helpful in designing those campaigns. And so these are the type of products that you put out during the campaign, like the animations of different pollutants. And you can see this is running in the loop here. Sometimes the air is really stagnant. Sometimes the plume kind of goes eastward from mainland China. Sometimes it comes southward. So you have to see, like, if you are planning a flight, in what region do you want to go? And if you're going into a particular region, what type of air mass you are likely going to sample? Of course, because again, the models have errors. These are just indications. So there are a lot of decisions that you have to make in flight, or when you are driving a van around, you have to make a lot of decisions that are for logistical regions. So the flight campaign are not completely dependent on the model forecast, but they are used as one piece of advice. Again, this is some CO tracers, like we were because we were sampling different regions, how the distribution, how the CO emitted from Philippines looks like at the surface, how the CO from Northeast China looks like at the surface, what is the contribution of biomass burning at the surface at 4 kilometers, because the biomass burning comes up with a lot of heat flux. So you may not see a lot of smoke at the surface, but you can see a lot of smoke in the upper atmosphere. Okay, all that was with MUSICA V0, means we were using the hydrostatic assumption, hydrostatic dynamical core to drive those simulations. Over the last year, we have started these simulations with MUSICA V1, where we are now using the MPAS non-hydrostatic dynamical core. And this is to look at the ECLIP field campaign. The objective of the ECLIP field campaign was to understand how Asian emissions are pumped into the upper troposphere and lower stratosphere because of the Asian monsoon. And so we are now trying to confront our model against those simulations. And again, this will look very fancy, but do not believe this is true because we have not compared it with measurements. this is just what we see in the model, right? So when I play this animation here, so these clouds that you see, these are carbon monoxide mixing ratios, right? And so this animation goes from July 27 to October 2nd, which is kind of the peak monsoon season over Asia. And you will see, like, I will just be quiet and I will let you watch this movie. So it's maybe a 50-second movie. And you will see very nice anticyclonic movement of carbon monoxide because of the Asian monsoon. And then at some point, this will become a vertical animation, and you will see how convection shoots up pollution plumes in the UTLS. So I'm going to play it now. I will be quiet until we have finished this animation. Speak now, but you see, it's very interesting that like towers of injection going into the UTLS. And so this is only possible in a global model because we go down to Asia at 3-kilometer resolution. We are able to better resolve emission sources at that resolution while still maintaining kind of a 60-kilometer resolution over the rest of the globe. So this is a capability that we have just started simulating. We have not evaluated it yet. We do not know how correct these simulations are, but this looks cool. All right, so this brings me to the final component of my talk. We are actively developing the MUSICA ecosystem. And so this I showed this slide. We already have two configurations, MUSICA V0 and MUSICA V1. And so this is how this works in a software world. It is a very high level overview. So what we are doing is we have the MUSICA library, which is written in the C language, but then underlying the gas phase chemistry, which is done by model independent chemistry module MECM. The photolysis model, these are written in C++. And then we still have to work on the aerosols part. We have been focusing on the chemistry part within the MUSICA library. In the previous simulations that I showed, we took aerosol model from CESM, but we are building an aerosol model within the MUSICA framework. Then what we are trying to do is, the goal is that this MUSICA interface can be coupled to any model. And so right now we are coupling it with, NOAA is coupling it with their model, which they call as CAT-CAM. And sorry, I do not remember the acronym for that. And then we are trying to couple it with MPAS, the model for prediction across scales, the atmosphere component, because it's great to have an Earth system model, but not everybody had supercomputers that NCAR has in the world. So people need a simplified model that maybe can work only on the atmosphere. And that is the objective. And this is where we are collaborating with Sachin's group in implementing chemistry in MPAS-A, which will be a replacement for the WRF-Chem model. Then we also have a box model. The box model that I talked about in the beginning, you're just thinking about this room, a music box. It's a model that you don't have to download. You can go on the website and run this model. You can go on this website that is listed here, and you can provide concentrations of different species. I think you can also add more species if you are interested in making it a more complex chemical mechanism. And then you can provide environmental conditions, like what is the temperature of the box, what is the pressure of the box. You save it and you can run it. So what it will also do is, when you list these different species, it will also provide you a flow diagram of the different chemical pathways. So you don't have to do it yourself. If you want to put it in a presentation, then it is already done for you at the website itself. And then finally, we are developing a model evaluation framework, right? Means as we start our PhD, we all write our own codes to compare models with the observations. Sometimes we make errors. We make those errors by mistake. We do not discover them sometimes until we have published a paper, right? And then you find out there was a bug in your code. So we are developing a model evaluation framework that you can download. You can compare your model against all different types of satellite observations, all different types of in situ observations, aircraft observations, etc. So this is another tool that is in development. Here is an example plot of evaluation over the US. And if you go to this website, we recently organized a tutorial for this tool. You can go, you can download it, and then give it a try. If you find bugs, let us know. We would also like to learn from your experiences and improve this capability further. This is just kind of more the plans and goals for Melodies Monet. We want to make it accessible to any type of model. And then finally, this is where we are working with IITM right now. We are trying to put MPass chemistry within MPass A. Some of the progress is we have already added Go-Kart 2G bulk aerosol scheme, as well as a tracer option in the MPass A. MPass JEDI. JEDI is a data simulation system. So it will be a replacement of GSI, which we are currently using in the Delhi Air Quality Early Warning System. The MPass is already coupled to JEDI. There is a lot of developments happening for AODS simulation there. We are completing work on adding a fire plume rise calculation within MPass. So it will be based on the fire inventory from NCAR. And then we are working on the design of putting full gas phase chemistry into MPass A, collaborating with IITM, NOVA, and university partners to further advance it. The resources for this development are very limited currently. And so we are all voluntary workers here in this development. We are writing proposals. We are trying to find support for it. So we don't have a timeline yet when this model will be available, but we are trying our best to accelerate the development as much as we can. There is a MUSICA tutorial series. If you are interested in this model, go to this website. There are a lot of videos. Everything that we do, we try to document it, we record it, we put it on the website. You watch the videos, you try the commands yourself. But if you run and join this MUSICA list, the discussion list, because a lot of people join this list when they face problems, they send emails to this group, and then people help each other. Because we have limited number of people at NCAR, they can answer a limited number of queries. But the idea is that the community learns from each other. So join this list. If nobody in the community responds to your questions, we keep an eye on these mailing lists. If we look at these mailing lists every day, and if a question has not been answered for a couple of days, then we take that as a high priority and answer those type of questions. So it is a community model. It is developed. We are developing it for the community. We want to develop it with the community. So I invite all of you, if you have any interest in evaluating MUSICA, you are interested in developing MUSICA, please don't hesitate in sending us an email, express your interest. We would be happy to have you on board. We really want this one to become next generation community infrastructure for atmospheric chemistry research. And participation of people from different countries is very, very important. Because, say, for example, you are working in India, you know the Indian conditions best. People sitting in the US developing these models do not know the Indian conditions, right? So you are the leaders of science in this country. You know the problems that you have in this country, and you have to take that leadership roles to confront these models, to understand how well they are working, what are the problems in these models. So do not use these as black box, confront them, try to improve them, and give your contributions back to the community. So I think I have covered the rest of the things. If again, this is the barcode is for the MUSICA website. And means over the US, we have some output. Once we have evaluated some of the MUSICA V1 output, we will also make it available. It is available over Indian region. So please go ahead, use it, evaluate it. You don't have to run the model. You can simply use the output. So with this, I would like to thank you. And sorry, I didn't leave time for questions.
Thanks, Rajesh, for the very interesting talk on music, and surely we are all looking forward to it. Time for a couple of questions. Yeah.
Thank you for this informative talk. So MUSICA V1, as you said, it has a non-hydrostatic approximation in, right?
Yeah.
So does it not create gravity waves at night time specifically? And does it not affect the transport of tracers?
I do not know much about gravity waves, so I cannot answer this question, but I will ask my colleagues and get back to you.
Okay, thanks.
Yeah, sorry about that.
Yeah, hi. I believe the MUSICA still do not have explicit chemistry mechanism like WRFKM, right?
It has.
It has. So we have
So
different mechanisms to choose from.
Yeah. No. So we do not have so many chemical mechanisms that we had in WRFChem, right? Because we are developing it at NCAR. We understand the Mozart-based chemical mechanisms very well because we developed those. So we have Mozart-based chemical mechanisms in MUSICA.
Okay. And one of your slide, you have shown the emission, diurnal variation of emissions. So those emission inventories are available, or you just estimated those diurnal variation in the emission?
So that is specific for Korea, right?
Okay, so they have that data.
Yeah, they have that data.
Okay.
But some generalized diurnal variations are also available. Some studies have been done in Europe, but I am not aware if there is an India-specific diurnal variation.
Okay, one last question. So in WRFKM also we can have variable grids with nesting process. So how is it different than the MUSICA? How MUSICA is different?
The main thing is when the plume goes outside your outermost domain, right? That plume cannot come back into WRFChem, whereas it can come back in MUSICA.
Doesn't make it MUSICA more computationally expensive?
No. So that is the thing. See, it becomes more expensive when you only compare the cost of WRFChem against MUSICA, right? But for running WRFChem, you also need to run a global model, right? So when you combine the cost of two, then these are very similar. There is a question back there.
Nice, very interesting and very important talk. The real case conditions actually in the US actually we have seen in the California region over a very big area there was a wildfire, and it must have increased the temperature as well as the pollution level. So my two questions is that for your NCAR actually taken some observation to feed to your model to simulate that, number one. And number two, the policy decision makers, what they did to confront with that, because it was for a long period. Just like we have got in Delhi, there is a pollution problem for a long period. Mm-hmm. So what the administration did for getting rid of that?
So the answer to the first question, even though we have the assimilation capability in the model, we did not assimilate anything for that particular episode where we tried to simulate the Californian wildfires. The second is, so like IITM, we are a research institution. And so the agency that provides operational forecast in the US is NOAA. So we are doing research to advance the science. We work together with NOAA. We are trying to get these developments into NOAA, but our products are not directly used for decision making right now.
So, but what type of can you suggest something actually?
Yes. So, I wish I had my laptop. So, a lot of the numerical weather prediction models right now, and so first of all, let me tell you that we have large errors in our PM2.5 and ozone predictions during wildfires in the operational air quality forecasts. And those errors inhibit the ability of decision makers to implement correct decisions. NOAA has been funding a lot of studies, different approaches to address that problem. One of that is dynamical ensemble, right? You run an ensemble model with different fire emission inventories by perturbing the plume rise, by perturbing the anthropogenic emissions, because these fire plumes also interact with anthropogenic emission sources, and see if we can get a better prediction with a probabilistic approach. That is one thing that NOAA is funding. I lead that project. Then the second thing that another proposal that we have submitted is, we know that the fire emission inventory generation process itself is very uncertain. You look at the fire location from the satellite, you assume there is a particular fuel available to burn, and then you make assumptions about the emission factors, you make assumptions about like how much the fire is spreading, and then you create emissions. That's why these are so uncertain. So we have implemented a fire behavior model, which means that you ignite a fire into the model, you constrain the fuel load with the satellite data, you burn the fuel during the runtime in the model, and you try to create emissions and then provide that to chemistry. But that is only at the proposal stage. This may become available in future. And then the third approach that NOAA is exploring is how can we bias correct our predictions? There are statistical methods, there are machine learning methods now to combine model predictions with observations to improve the accuracy. So multiple efforts are going on. I would say we still haven't reached the level of accuracy that we want, but there are multiple efforts in that direction. Did I answer your question?
Thank you very much. For the mitigation process, what actually, just like in Delhi, there is a very long period that is a pollution. So somebody is telling that just like cloud seeding, and that can help. Any other technique which you can think that will be useful for decreasing the pollution level for a long period?
So I would say that the mitigation measures that are active in Delhi right now, or that are under consideration through the graded response action plan, those type of measures do not exist in the US right now. The agencies, they only use air quality forecasts to provide air quality alerts. They do not do any type of mitigation efforts. And I think for the Delhi, I think cloud seeding is kind of a misplaced solution that is proposed, because if you look at the long-term
proper
data,
location,
right? Because even if you have a rain episode, within like one day, you get back to the level where it was. So I think the emission mitigation, a proper analysis of what is really contributing to pollution in the Delhi airshed, not just Delhi. We need to look at the Delhi airshed.
This has to be decreased.
Exactly. We need to come up with a long-term mitigation plan.
Thank you very much.
I have just a small question.
Yes.
I saw that you have used monoxide emissions from MOPIT, I guess. Have you also used OCO2?
So the MOPIT is providing carbon monoxide concentrations, not the emissions. But when we are looking at air quality predictions, we have simulations that go for a month or maybe maximum a year. And so CO2 is, you can treat CO2 almost as inert at those timescales.
Just taken the monoxide from MOPIT.
Yes.
But can you also take it from OCO2? Have you tried from OCO2?
OCO2? No, we haven't tried from OCO2. We are only assimilated carbon monoxide from MOPIT.
Okay. Rajesh, very good work. I mean, it's nice to see MUSICA come along so far from where it started. A couple of questions. So you seem to think that the resolution plays a very important role, and in some cases it does show it. But clearly the mismatch is still there with observations. So doesn't that very clearly tell you that it's not a resolution issue, but it's a chemistry issue?
No, I think it's a issue of both, right? It's not just chemistry, it's also the physics, right? If we do not understand the stratification of boundary layer well at night, it's a physics problem, right? And so there is if there is a error in the PBL parameterization, how you are doing your mixing during day and night, you are going to have errors in the chemistry.
I would completely agree with that if that was the same problem for your primary and secondary pollutants. But considering you're getting a bigger problem in your secondary pollutants, that most likely is a chemistry issue, right?
Yeah,
so the processes.
Yeah, definitely.
Okay.
I mean, because you see that we have thousands of VOCs in the atmosphere.
Yeah.
The way we try to represent VOCs here, we simulate ethane, propane, and then everything that is bigger than butane, we lump them into bigger alkanes, right? So there is, depending on the structure of the molecules, their reactivity is different. And you are assuming that everything that is bigger than butane has the same reactivity. Everything that is bigger than butene has the same reactivity. So those details are missing from the models. That's why all models are wrong, but some are useful.
Just a follow up to that, unless somebody else has a question, is you were talking about resolution again and trying to run a global model, but the lifetime of most of these species is really small. Why would, if I wanted to do an experiment over India, why would I want to run a global model for that? Just to get like some plumes coming in, but with boundary conditions, you can solve most of those issues. And computationally, it would be a lot more expensive, right?
No, I think so. The reason is not just air quality, right? So look at the UTLS. So the transport of ocean emissions, if they go into the UTLS, they are going to create tropospheric ozone, right? That is going to have a climate signal later, because the ozone lifetime in the troposphere is more than a month.
Sure, but for a climate signal, why would I want such a high resolution model?
Because you want to resolve the emission sources and the transport of those emissions. You want to have more accurate simulations of the chemical composition of the upper troposphere, where the greenhouse gas effect is the most efficient.
Okay, maybe we can discuss this offline a little bit. And the other question is, so now MUSICA is doing well. For it to become like a proper ESM which scales, are there plans for other modules to do the same?
Which modules?
For example, your biogeochemistry, etc.
I do not know about that. I'm just concerned about the chemistry part here.
Okay. If there are no more questions, let us